Hi, let's talk about the radar range equation. Let's talk about CCMP's wireless designs. Let's talk about setting up our success for hacking into wireless networks, especially laying down the ground rules for site surveys and what it'll look like in the future. So, if you've cut, if you've touched the CCMP or you've done anything with Cisco's wireless certifications, then this picture up here is very familiar. I've omitted the different decibels associated with the transmitter cable, the antenna. In this case, I picked a parabolic antenna. But essentially, you'd be calculating the amount of power that would have to come from this system in order to receive a certain signal sensitivity at this particular antenna. And what would happen is you'd be given the cable loss in decibels, you'd be given the antenna gain in decibels, and you'd be given the transmitter power in decibels. Then you might have to figure out what this free space loss is or free space propagation decay in order to get a particular signal noise on the right side. And Cisco makes it very easy by looking at the decimal values associated with a high level. Okay, here's the antenna gain, here's the cable loss, here's the free space propagation decay. But it all comes and is derived from the radar range equation. So since we're hackers and we want to hack into, different endpoints or Internet of Things, we may have to go down to a lower level and actually figure out what the particular radar equation is for that end device. So whether it's a cellular device or whether it's a network device or a mobile device, we would have to figure out the ins and outs of the radar range equation or the radar equation. And in this scenario, we'll go through a very basic example and we'll derive the generic radar equation. And so there's two different types of antennas to be concerned about. You have your directional antennas and you have your omnidirectional antennas. Or for omnidirectional antennas, you have dipole antennas. For directional, you have stuff like patch antennas, which I used over here. You have Yagi, you have parabolic, and you have ever different types of antennas. So when you're talking about omnidirectional antennas, essentially you're looking at isotropic antennas where the signal is covered in a 360-degree manner uniformly. And when this happens, you're essentially using a basic physics shell theorem that spreads the waveforms out uniformly, and you can calculate it from the following equation where you're looking at the transmitted power on top, so the transmitted power from here, and it's decaying exponentially, r squared, and essentially you would also have to calculate the shell part of it, which is going to be a sphere, which is for area of a sphere is like 4/3 pi r squared, pi r cubed. And so you have to take that into consideration. Going further, when you're looking at directional antennas, you take this shell theorem and you try to transmit with as much gain as possible. And what that means is you're looking at one specific area. So before we talked about azimuth and elevation, well, you're looking at one specific azimuth and elevation, and when you transmit, you're going to have different notches or lobes associated with side channels. But we're looking at the main beam in this scenario, and for the main beam, you're going to get the gain by subtracting it from the uniform or isotropic region that normally would happen. So essentially, For our parabolic dish up on the top left, you have a uniform or isotropic shell right here, and whatever main lobe goes beyond that isotropic shell is going to be the gain associated with it. And so what Cisco gives you on their certification is they give you the decibels for the gain of the antenna, and that gain is just figuring out how far the main beam is from the isotropic shell. And that's really what you should be concerned about here. So let's go through and derive the radar equation. So we talked about part of the radar equation right here associated with the isotropic shell. You also have to be concerned with the gain. So the gain's going to come from the main beam, not necessarily from the side lobes and the notches. So you can then tag on the gain associated with it. When you're looking at directed antennas and you're looking at how much signal you're going to get back to your system, then essentially you're looking at not just the gain but the RCS associated with the target's antenna or target's radar or target's vehicle or whatever you're concerned with, whatever the target is. In this scenario, we're looking at smart cities or enterprise endpoints within your warehouse. And so a patch antenna would also have an RCS. In this case, it's going to be sigma over 4 pi r squared. And that's the reflected value back to the original transmitter. And after that, you have to also be concerned with the area on your original transmitter. And we'll go through what that means later. And so that's just going to be the power received back from your patch antenna based on the parabolic antenna's original transmit. And so we also need to be concerned with the total losses that are inherent of the system. We also have to be concerned with Boltzmann's constant. We also have to be concerned with the noise bandwidth of the receiver. So the background noise like cosmic rays and other things like that. And that will help derive the bottom part. So consider this all to be, noise that takes away from our received signal that's transmitted back from the patch antenna. And you also have losses associated with the system that's inherent within any radar system or parabolic antenna, transmitter, cable. That's the stuff we calculate on the Cisco exam. And so, hi, sorry, my phone cut off while I was filming this. I've been making so many videos lately that the storage overflowed. So I'm restarting from halfway through. I apologize, this won't happen in the future. But we left off looking at the bottom or the divisor. And essentially what we came up with was the Boltzmann constant. We talked about the temperature associated with the system or the system noise temperature. We talked about the noise bandwidth and the total losses inherent in the system itself. So after this, I then went through and I made it easier. I simplified the terms. I looked at signal noise ratio, or S to R, as some people write it. So S divided by R, or signal noise. And what we essentially looked at calculating the power received over any type of loss. And we simplified the terms, but we haven't looked at the area associated with the antenna coming back from the received signal. To make it easier, we looked up the affected aperture associated with antennas, or the generic formula, and that's going to be the gain times the wavelength squared over 4 pi. If we simplify the terms even more, we essentially come up with a signal to noise ratio, which is the radar equation of the transmitted power times the gain squared times the wavelength squared times RCS associated with your target, divided by 4 pi to the third power times R to the fourth times the Boltzmann constant times system noise temperature times the noise of the bandwidth times the internal system losses. And so this is going to be the final equation associated with radar antennas. Now, one thing to harp on, and wanted to show you guys a little more about this, is let's erase this side and look at what signal and noise looks like from a Cisco perspective. So they list out stuff like this. So you consider this the floor noise, and here's your signal, and essentially what you can calculate is your signal and noise ratio associated with your signal to the floor noise. You can also see it sometimes like this, where you're given, you know, a bunch of signals and stuff, and then you're given your floor noise. So that's your floor noise, and this is your signal. You then can calculate your signal to noise ratio associated with that. So once again, there are a lot of tools and technologies that help alleviate calculating these by hand, or even having to write a program to calculate it. However, when you're a hacker, you don't have this for all the different types of systems or technologies you're hacking against. And quite frankly, they don't want you to have that stuff. So you have to be familiar with the radar equation in order to calculate accurately whatever end system you're looking at, or whatever IoT device or antenna you're looking at, so that you can effectively implement side channel attacks and other things like that. Once again, I thank you for your time, and I hope you have a great day. Bye.